I'm going to do an overview review of Unit 6 for AP Chemistry, which is thermochemistry. This will probably be a multi-parter. So let's start with a little bit of vocabulary. Exothermic reactions are reactions in which there's a negative delta H. That is where heat flows out. Graphically, it is going to look like this. So your reactants are going to be higher than your products, and when you do that subtraction, products minus reactants, you're going to get a negative delta H. Endothermic is the opposite. With endothermic, your sign of delta H is positive, which means heat flows into the system. And then in this case, your products are going to be higher in energy than your reactants. Heat transfer occurs when warmer, which are faster moving particles, collide with slower, cooler particles. And then eventually that heat transfer will cease when they are both at the same temperature, which is when you have reached thermal equilibrium. The majority of Unit 6 deals with enthalpy, which is delta H, which is expressed in units of joules per mole or kilojoules per mole. So we're going to look at all the various ways you can interact with enthalpy and calculate it. So first with calorimetry. So calorimetry uses the equation Q is equal to mc delta T. Q stands for heat, M is mass, C is specific heat, delta T is the change in temperature. And when you're doing a change, you do final minus initial. Sometimes we set those two equations equal to each other so that something that is initially hot is put into something that is initially colder. Often this is like maybe a metal sample, and this could be water. In that case, with calorimetry, or in all cases with calorimetry, we're assuming that all of the energy is contained within your experimental setup, sometimes even just a coffee cup. So all the heat that is lost by the hot thing will move to the colder thing, and that means that your final temperature will be the same because we have attained a thermal equilibrium. If you're doing this situation, you could solve for specific heat or one or the other, a temperature value, mass, and so on. In this case, your units is going to be, Q is going to be in joules, M is in grams, specific heat is in joules per gram degree Celsius, and then your delta T is going to be in degrees Celsius. When you're studying solution formation, your mass value up here is going to be equal to your grams of solute plus your grams of solvent. So for example, if you're dissolving something in water, you're going to take the mass of the thing you're dissolving plus the mass of the water and add them together. You're going to do that before you plug in Q equals mc delta T. Calorimetry is based on the law of conservation of energy, which says the energy is conserved, what goes in must come out. Usually when you're supposed to do a problem with calorimetry, you're going to be given the specific heat and or temperature data. So that's a clue that you're doing calorimetry. Calorimetry is also used on heating curves or cooling curves. This is a heating curve. A cooling curve would look exactly the opposite. So this is going to be your temperature, and this is going to be your progression of the process. Your delta H of fusion, which is called the molar enthalpy of fusion, is the amount of energy that's required to change a substance from solid to liquid or vice versa. That is this point on the heating curve. Anywhere you're on your vertical part of the heating curve, you're just heating a substance. Here it would be a solid, and you're heating it up. Here's a liquid, you're heating it up. Here's a gas, you're heating it up. On the flat part, you're actually doing the phase changes. So this flat part is vaporization, from molar enthalpy of vaporization. So that is going between liquid and gas, for example, boiling and condensing. So in these rising parts of this graph, you're going to do Q is equal to mc delta T. Here you're going to do calculations with delta H of fusion or vaporization, which you can really just treat as a unit conversion. Sometimes you have to do two or more calculations and sum them. For example, if you're going to heat up a solid and then fully melt it, if you're going to heat up a liquid and then fully vaporize it. Usually you're given information about the heating or cooling that you're doing and or phase changes.